Hopping over, and I'll introduce the next speaker. Nathan Bailey. He's going to talk to us about Wankel rotary engines for aerospace, propulsion, and energy systems. So Nathan is the Managing Director of Advanced Innovative Engineering in the UK and is a pioneer in Wankel rotary engines. He's got an unwavering passion for innovation, particularly in Wankel technology. So I've known him for about 8 years now, from my previous existence. I started work on Wankel engines very many years ago. And we had a joint project at the University of Bath looking at range extender applications.
Don't need the Bluetooth there.
I'm well aware of what he's doing in aerospace, in drones, and we are going to be putting a Wankel engine on our test bed to look at applications for mainly drone use with renewable fuels. So with that, I will hand over to Nathan.
Thank you. Okay, the microphone's working, that's good. Thank you, Professor Turner. And thank you for KAUST and the CCRC for inviting me to present on Wankel rotary engines today. So a bit of a change or a shift in pace from some of the other presentations. This one, I guess, will be more of a sort of overview and sort of more application driven than necessarily a sort of deep dive technical or discussion on specific technical issues. So Wankel rotary engine. It's been around for a long time. Oh, this was working. Oh, okay. Okay, use the manual. I'm Nathan Bailey, so the founder and managing director of Advanced Innovative Engineering, as the great introduction Jamie gave me said, and I've been working in rotary engines now for about 25 years. So it's one of those technologies that when you move into, you either get infected by the bug of rotaries or you don't. Some people sort of, transit through them. Other people work within rotaries and then they just find the whole technology fascinating, the applications fascinating, and you sort of tend to get stuck, which is what happened to me. So the presentation today is, as we said, is to discuss really, I suppose, Wankel engines in aerospace applications. It's one of the applications that is probably least known for rotary engines or IC engines. Obviously, most aerospace is turbine, but there is obviously an area of the market below turbines. Turbine, I think, is accepted as being absolutely the best solution for larger aircraft. But when you start to come to smaller aircraft, particularly uncrewed or drones or whatever you want to call them, then obviously there's a big space below turbines where the IC engine can still sit, and the rotary engine in particular makes an ideal fit for that. AIE is a business. We're in the Midlands in the UK, just outside Birmingham. It's a great location if you're developing technology. It's obviously got a massive history in engineering from the car industry, from Rolls-Royce, which are literally just down the road, and a lot of other big sort of industrial manufacturers and development institutions. So yeah, it was a logical decision to sort of base ourselves in that location. It's also where I lived, so it was really handy. So within the team of AIE, we actually pulled together a sort of combined experience of about 80 years in rotary engine development. So we were very fortunate because the rotary engine world is small. There aren't many companies in the world working on rotary engines, and there's very few engineers actually working in rotary engine development. So it's an area that sort of stagnated really over the decades. And our goal really is to deliver an exceptional product. So we do concentrate on that one technology, but the goal is to excel in that one technology and deliver a great product to our customers. So when we set up AIE, we decided that we didn't want to just as a lot of other companies do, take an existing rotary engine technology or take a Mazda engine and chop a rotor off it and modify it or do anything like that. We said, no, we're going to clean sheet. Between us as a team of engineers, we've got a huge experience in operating rotary engines in predominantly military applications, particularly in some of the conflicts over the last few decades, where we'd accrued somewhere in the region of 3 million flight hours of experience with rotary engines in aircraft. So we wanted to take all the information that would gain from those flight hours and clean sheet some engines and redesign them to try and design out the limitations, but design in some other positive attributes for the engine. So when we set AIE up, we said we need to go for the full spectrum. So all the way from that sort of concept clean sheet design, conceptualizing technology, including developing new patents, which we do, all the way through to production. Production for UAVs or for small aircraft is not high volume. You know, we're not talking, you know, tens of thousands of engines a year. Production in this sort of aerospace niche that we sit in is, you know, a couple of hundred engines a year. So it's quite a nice market, but it's a high value market as well. So it works well with a smaller team like we are. Through the sort of arc there, you know, we do, like you say, we do clean sheet, we do the research. We have 4 PhDs working for us at the moment. We have a big suite of software to help us design and develop, including what were formerly Ricardo products, but now called Realis Wave, Vectis. We use ANSYS CFD, both Fluent and CFX. We use Entopology for topology optimization. We've invested very heavily within that sort of analysis space, and obviously invested in the people as well. And then also through to the sort of design prototype side, we've also invested quite heavily in test cells. So we have 2 Froud dynamometer test cells, complete with sort of AVL fuel weighers and sort of Hariba mixer emissions analysis. So actually, as a small company, I mean, we're 22 people. As a small company, we've got a lot of equipment and a lot of facility for the size of business. Moving down through the sort of production side, we have actually now split out our own manufacturing company as well. So we have a sister company alongside AIE that does the machining, manufacturing for us. So we concentrate within AIE as a company on the development of the product, the testing of the product, and that final delivery to the customer. The range of engines for rotaries, again, rotary engines, most people associate them with a sort of certain size, which tends to be the Mazda engine, which we'll talk about in a bit. But rotary engines can exist, you know, in a wide variety of sizes, capacities. You're not really restricted, other than some of the fuels can start to restrict the capacity of the engine. But yeah, our own range, we go down to the 40cc engine. So literally, this is an engine that you can hold in your hand, weighs 2 pounds. I mean, sorry, 2 kilograms. I wish it was 2 pounds. 2 kilograms. It's tiny. People don't really believe it's an engine. All the way through to the 650, which is slightly larger and has been used in a number of larger applications. But it's, yeah, so we can do the full range. There's no real sort of scaling limitations there. Customers that do use rotary engines in the market, we've worked with a lot of them. This isn't exhaustive by any means. So there are a lot of rotary engines in aerospace applications currently. I know a lot of them flying around the world as we speak. But again, it's this sort of niche that nobody really hears a lot about, but it's there, and a lot of the larger companies in the world have invested in this technology. So rotary engines, I'm sure a lot of you know what a rotary engine is anyway, but a lot of people I talk to don't know what a rotary engine is. So it's always useful to have a slide, which I think was cribbed off one of Gio's slides on the former presentations there. But it was very useful to sort of highlight the various aspects of the rotary. So picture on the left is a sort of typical Mazda-esque type engine. Housing on the outside, triangular rotor on the inside, and a sort of trochoidal shape in the middle. You can see from the motion on the right-hand side that it rotates. There's no stop starting. It's not reciprocating in any way. So it's good that you've got the continual rotation, but it is on an eccentric. And also that the various stages of the process happen in different areas within the engine, which can be a positive, but also can be a challenge. Whereas obviously in a reciprocating engine, everything happens within the single cylinder in the same space. So this can cause some issues with things like thermal balance. You end up with a very cold side of the engine on the intake, and you end up with a very hot side of the engine on the exhaust. So if you're using lightweight materials such as aluminiums, you know, trying to get that engine not to twist with those sort of thermal differentials, you know, to make sure your sealing surfaces work very well is a bit of a challenge. And there's various technologies and various techniques you can do to overcome that. One of the main advantages of rotaries, because of this rotary motion, though, obviously, is that they're fairly well balanced in comparison to reciprocating, so vibration is very low, and also that the sort of power stroke is over a much larger angular degree of the rotation of the engine. So this is not the entire history of rotary engines by any means. So I've just put this slide up there to sort of show that the engine is obviously not new. Felix Wankel, in the 1950s, sort of had the concept, but I think it's fair to say he sort of got a concept that worked, but then it was really NSU that took the engine and really made it work properly for applications. NSU are obviously one of the famous sort of rotary companies. Mazda probably being, the most famous because of the ones that existed in the sort of automotive space in recent years. But the actual sort of technology heritage that we follow, so there's, as with all technologies, you have this sort of initial idea and concept, and then it branches into multiple and different branches. One of them went the sort of automotive route, the oil cooling of the rotor. The branch we follow was initiated in the sort of 70s, 80s in the UK, which was the sort of air cooling rotor branch, which actually gives you a sort of lighter, simpler rotary engine than the air-cooled version that you see in automotive applications, because you don't have the sealing rings, you don't have the oil lubrication system trying to cool the rotor down in the center. You have this sort of very lightweight, simplistic engine, which is great for aerospace, but then brings us other challenges. But again, nothing's for free at the end of the day. So yeah, I mean, AIE itself was formed in 2012. And really, as I say, we were sort of building on this heritage through the UK arm of the technology with regards to this, what's commonly known as the air-cooled rotor engines. Application-wise, as discussed, everybody knows Mazda. Most people know NSU, if you know about cars. But rotor engines have been used in literally everything by everybody at some point in history. So in the 1960s and 70s, it was seen as the sort of replacement for the reciprocating engine. There was a huge amount of excitement about the rotaries, and every major car manufacturer and motorcycle manufacturer in the world picked it up and decided that they were going to do a rotary engine because it was so much better, including companies such as Mercedes, General Motors, obviously a lot of the Japanese bike manufacturers, jet skis, snowmobiles. I mean, like literally everything you see an IC engine in today at some point has probably had a rotary engine in it, and it's been experimented with. The sort of implosion of the rotary sort of happened in the 1970s. There was this sort of brief period of massive expansion and development, and then in the 70s, it sort of most manufacturers decided actually it wasn't for them based on a number of factors, one of them being the oil crisis in the 70s and the cost of fuel. At that point, the rotary engine was nowhere near as efficient as a reciprocating engine, so I guess the calculations were, why are we pursuing this technology when it doesn't do what our engines, our existing engines already do? But there were a few sort of champions that continued with the engine development. One of those was Mazda, as mentioned again, and then the other one was Norton in the UK, which again is where our heritage comes from for the motorcycles, looking for a differentiation technology from maybe the Japanese bikes, where they couldn't compete on cost or volume. So they were looking for a technology that inspired people, was a bit left field. The rotary engine sort of fit that bill. And then as you see more recently, since the 1980s, the sort of also development of the sort of aerospace arm of rotary engines, particularly in the sort of uncrewed or sort of drone aerospace. So a lot of vehicles around the world using these engines. So benefits. So multi-fuel isn't just a pure benefit of rotary engines, but rotary engines can run on a variety of fuels, in case most fuels. So that is a benefit when you're looking at different applications. They are extremely compact, as I say, from an engine that can sit in your hand. The 650 engine that produces 120 horsepower, you can quite easily hold with two hands. We did various automotive projects where we attached the 650 to a gearbox, and people thought it was a gearbox. They didn't actually realize there was an engine on the front of the gearbox. They're extremely small. Again, low vibration. Again, you haven't got the reciprocating motion, so you are rotating, so the vibration is naturally lower. They are long endurance, and this is one of the things that people, particularly with the history around Mazdas, et cetera, see as a sort of massive negative. They consider the life on the engines to be quite restrictive, but it's actually not. You tend to find that rotary engines exist in applications that have very high power requirements, so therefore the engine is being driven extremely hard, which obviously for any engine reduces the engine life, unless it's over-engineered. But then when you're trying to make a very lightweight product, the two don't match together. So actually, they stack up. They are a reliable engine, and they do have a long endurance. They have very few moving parts, so logistically and manufacturing-wise, they're very simple to manufacture. They're very easy to support if you're in the field, because, fundamentally, you've got a couple of rotating components in the engine. Everything else is static. They do have a very high power-to-weight ratio. Again, you're getting 1 power pulse per rotation, so you're very power dense. And then they have a very progressive failure mode, which sounds a bit strange because failure modes are never good, but basically a lot of the applications that rotaries have been put into have really been dominated through two-strokes, or the two-stroke is the volume engine in that market, still, even today. And obviously two-strokes have quite sudden failure modes. So actually having an aircraft with a sudden failure mode is not desirable. Rotaries do let you know when they're starting to go wrong. You know, their power degrades over a period of time. There are indicators that the engine's not happy. So you don't have these sort of sudden stoppage sort of failure modes, which is important in aerospace. So the perceived disadvantages of rotaries, though, so obviously those are some of the advantages. The typical perceived disadvantages of rotaries are oil consumption. So obviously everybody thinks that, you know, rotaries drink gallons of oil. They do drink oil, there's no denying it. Exhaust energy, typically, particularly with our strain in the technology, we use peripheral port exhaust, and you do get a lot of exhaust energy. The exhaust is extremely hot, 950 degrees, you know, there's a lot of pressure on that exhaust. So yeah, it's a challenge, particularly when you're trying to, you know, reduce the noise signature of the engines. You've got to have the pretty hefty exhaust system to bring that down. Efficiency, again, people perceive rotary engines as being less efficient. Again, this is sort of historic from maybe some of the automotive applications. Manufacturing costs, but the manufacturing costs are driven by volume. You know, rotary engines have never really been manufactured in any volume in recent history, other than probably Mazda, and they ceased production in 2012. And I think their peak sales of the RX-8 were 12,000 cars a year, I think. So in automotive terms, that's nothing. So the manufacturing cost is driven by the low volume nature of the engine. So that's what drives that cost up. And then the time before overhaul, again, this sort of specter that, you know, the rotaries are somehow fragile and need to be maintained and, you know, are sort of, you know, require a lot of overhaul. Again, this was driven a little bit by automotive. So a lot of the sort of the negative perceptions of rotaries has been driven by using rotary engines in standard automotive configurations, i.e. coupled to a gearbox, trying to drive it in day-to-day operation, which is not what the engine is ideally suited for. So it's not the ideal engine for that application. Where the engine is more suited for is applications where it runs at a fairly constant power, is not connected to a mechanical drivetrain, has the opportunity to exploit its positive attributes rather than its negative attributes. So looking at some of the challenges with a rotary engine, it's easy to see them when you see the engine rotate through a combustion cycle. Obviously, you have this triangular-shaped rotor in the center. You've got a lot of sealing surfaces with a rotary engine. You have typically the tip seals, or the apex seals as we call them, which are the seals, again, that most people refer to when they think of Mazda, or do your tip seals wear, is the standard question from every customer that we ever approach. You also have a small circular seal in the, on either end of the tip seal, which we call the corner seals. And then you have side seals. So these are longer, sort of curved seals that sit on the sides of the rotor. So you have 6 of those, 6 corner seals and 3 apex seals. So it's quite a complex sealing surface because of the design and the geometry of the engine. So yeah, you've got a challenge there to make sure that obviously the leak paths are maintained, minimized. You don't want to maintain them. You do want to minimize them. So the leak paths are minimized to keep your efficiency up. You're not losing gas through the process. You also have to sweep past open orifices in the engine, such as the spark plugs, the ports, etc. So you have this opportunity for gas to escape around the seals in these locations. So yeah, there's a challenge. You know, it's not the easiest sort of engine to work with in order to get efficiency higher. So rotor sealing is definitely one of those. Life with regard to the rotor sealing is really been addressed through modern technology. So typically, obviously, people were using sort of cast metals for seals, etc. Use ceramics. I mean, ceramics are highly available today, and there's a wide variety of them, and ceramics have really solved this sort of tip seal wear issue, inverted commas, for rotary engines. Rotor versus flame front speed, so this really comes in with regards to different fuels. So obviously, as you can see from the animation, you inject, well, and this is actually a port-injected gasoline engine, just for demonstration, but you're injecting the fuel in, the rotor's got this continual motion that goes around, you're then compressing that and then moving it through to ignition. You can have a situation where obviously you don't get, or combustion doesn't take place fast enough, and therefore the rotor can actually catch the flame front up in effect, and you can get this sort of weird effects with inside the engine and incomplete combustion. So depending on the fuel you're going to be using, it really depends on this, it starts to limit the engine with regards to capacity for sure, but then also with regards to RPM. So several attempts have been made at running rotary engines with heavier fuels. We run heavy fuels of kerosenes, but you do start to become sort of RPM limited or limited in other ways with regards to that aspect. Lubrication, as I say, so again, you've got a lot of sliding surfaces in a rotary engine, including the side seals, which are quite big areas. So you've got to lubricate these in some way. So one of the ways to address that, again, is through ceramics. So again, we have ceramic coatings on the end plates. We use a ceramic metal coating on the rotor housing. We use ceramic seals. You can reduce your lubrication down to a bare minimum. We also don't inject oil anymore, so a lot of the early rotary engines used to actively inject oil, like a two-stroke, to lubricate the seal pack. We don't. We allow the oil to migrate through from the air cooling system, so minimizes that oil consumption again. And then you do have this phenomenon of port overlap. So again, this is the nature of the engine, this type of engine we do, which is the sort of peripheral port intake and exhaust, is the fact that at certain points in the cycle, both ports are open. They're actually connected. So that can cause challenges with efficiency, where you can see your fuel going out your exhaust before it's been used, and various other things. But this has now been mitigated through exploring things like direct injection. Obviously, where you can control the fuel goes, you can make sure it goes in after you've closed your port. So these, again, some of these, not modern technologies in automotive terms or reciprocating engine terms, but technologies that we're bringing into the rotary engine to make it more efficient and to just generally improve its ability to operate on different fuels. So why aerospace? So why is aerospace such a good fit for a rotary engine? And it really has found its niche in aerospace. You know, this is the market that's really, it's been going since the 80s, so it's really sort of a strong market. For all the reasons that make it a good engine, really, when you look at it. So the power density is obviously key. You know, when you're looking at small aircraft, power density is always probably the #1 challenge next to reliability and safety. It has a very small form factor, so these engines are physically very small, which makes them very easy to integrate into aircraft, particularly small aircraft. Obviously, having a big engine in a small aircraft is a challenge. They are low vibration, which means you don't need complicated mounting systems inside the aircraft. You are able to bolt these engines to the vehicle structure. We know AV mounting, which again is something that we have lots of conversations with our customers around. They used to do a lot of 2-strokes, 4-strokes. They used to have big sort of, you know, elastomer mounting systems, and we say, no, just get rid of all that. Bolt it straight to the aircraft. They are fuel efficient in comparison to some of the other technologies in this market. Again, we're talking small capacity engines here. So relatively, they stand up and compete against, you know, definitely compete against the 2-strokes and some of the 4-strokes. And for turbines in this market, when you start scaling those turbines down, they become less efficient. So actually, the rotary engine is far more efficient than turbines operating in the same power sphere. And again, we tend to find most of our customers come to us because they've either tried to experience using a 2-stroke and they have a huge amount of vibration and fuel consumption, or they've tried to use a turbine and they just can't handle the fuel consumption. So we end up in that sort of middle space. Reliability, as I say, progressive failure modes, and they are reliable as long as you service them within regular intervals, which obviously is standard sort of practice in aerospace. But the multi-fuel operation is very interesting. So the latest generation of our engines, for instance, can operate on multiple fuels with no physical modification to the engine, and in fact, no map change. More recently, we're delivering fuels now with a singular map, and you can run gasoline, avgas, kerosene, all in the same engine with no changes, no modifications, which is obviously, you know, for the customer, it gives them fuel flexibility, particularly when they're operating in remote areas and not typically from bases. And then ease of maintenance. A rotary engine, one of our engines can be taken apart and put back together again in the field with a very limited tool set within 4 hours. So we actually, and we've done quick release versions, or should we say sort of pallet load versions of the aircraft, and we've had customers who can actually change an entire powertrain within 15 minutes. So if you've got a vehicle that comes in and lands, the engine's got a problem, literally within 15 minutes, you can have that off, and you can have the next engine in, and the vehicle can go back out again. Probably a shorter time than it takes to refuel it. So what we're finding in aerospace is it's changing. So there is more interest in this sort of smaller sector or smaller end of aerospace now. This is being driven by whatever you want to call it, so advanced air mobility, urban air mobility, so this sort of some desire to have small aircraft to move goods, cargo drones, whatever you want to call them, or people, air taxis around in urban environments, or in actually the exact opposite, in environments where there's large distances between civilizations, so Alaska, Canada, Australia, you know, where they typically would use a 2-seat sort of standard aircraft. People are now looking to sort of uncrewed vehicles to do that job instead. And then obviously, as soon as you take the people out and you've removed the weight of the people, then actually the vehicle size can come down, the vehicle weight can come down, so they start to look at every aspect of the vehicle, looking for a high power dense small engine to provide that. Hand in hand with this, you're seeing this sort of desire now to have multi-rotor applications. So traditionally, you'd have wings and a propeller, and now, or a single rotor disc like a helicopter. Now, most vehicles are multi-rotor. They're looking for electric propulsion, and then they're looking for the IC engine to provide electrical power in the heart of the engine. So, sort of hybrid situation with a battery pack. It gives you some safety cases as well. If your engine fails, you've still got battery to land the vehicle. If your batteries fail, your engine can still provide electrical power, so it gives you some safety case advantages. But it's primarily driven by the fact that most of them want to run these multiple rotors, and obviously having any sort of mechanical drive to multiple rotors is very heavy and very complicated. So stick electric motors on them, it simplifies everything. So we're seeing this big sort of push towards that sort of electrification of these aircraft, which is great because rotary engines love to operate at a single power point and deliver power. Thus, you can make them efficient, you can design them to operate efficiently at a single power point. And then also the push towards clean fuels. Less so at the moment. Most of our customers want to use kerosene. They want to use JP8, JP5 military fuels or Jet A1 for commercial fuels. But obviously there are customers coming in now asking for SAF, engines that can run on SAF, or the new aspect, and the one that we're really interested in, we're doing a lot of development with, or starting to try and do some development with, is hydrogen. Challenging for us as a small company because of all the reasons of bringing hydrogen into our own company for test cells and et cetera. So this is where we're pairing up with universities or research institutions to actually explore that hydrogen aspect of the engine. The rotary engine also potentially has some advantages running hydrogen over reciprocating engines because of the elongated combustion chamber shape. The high flame front speed of hydrogen is a real advantage in a rotary engine, as opposed to liquid fuels where it's a challenge. And then it mitigates other things such as knock that you would see in other engines. You're starting to move, yeah. So then when you look at the overall picture, I'll race through this a little bit then. So basically, really I covered this in the last slide in my discussion, but you've seen this convergence of requirements that actually making the rotary engine even more relevant in aerospace. The drive towards electrification, the desire to have multiple fuels, including biofuels and clean fuels, the fact that everybody wants to create. So the engines are now moving from the back of aircraft or nacelles under the wings to the inside of the aircraft. They're actually wanting to put these engines inside the fuselage, which means you need a compact, small, low vibration engine in order to do that. And then finally, work to be done. So as ever, engines are in constant development. So cooling is always a challenge for rotaries. Power dense engines, small, aluminium, keeping them cool is always a challenge. We have some patented cooling technology called Sparks, which really does give us an edge in this. It's why our engines stand out from a performance perspective. Direct injection already mentioned, particularly more relevant as you move to different fuels. Forced induction, talking to people yesterday, there's always this big dilemma around forced induction. Forced induction for us really is around altitude compensation. You don't really want to drive more power density into the engine because we're pretty power dense anyway, and then you have a thermal challenge to try and reject the additional heat. Improved lubrication, everybody wants the engine to use less oil. So obviously, lubrication improvements are continuous. Compact generators, ceramic materials, and then one of the interesting technologies I'm very interested in, and I know Jamie's interested in as well, is the exhaust expander. So having this second chamber to allow the exhaust to continue to expand and to recoup energy from that, because there's still a lot of energy in that exhaust when it leaves the engine, so just to recoup that energy back. Also gives you improved exhaust emissions and also exhaust signature, acoustic signature. And then obviously this is all sort of coming together with some of the advanced modeling technologies that we're able to use now and additive manufacturing. And then this is the last slide. So just to give you a real world example of a current project, it's actually very dark, so I apologize about that. But this is actually a business jet APU. So I didn't realize because I don't own a business jet, but apparently most business jets of a certain size don't have an APU on because they've never found a turbine APU that's small enough to package within the envelope of the aircraft. So there's this big sort of open market for APUs, and it's particularly been driven now by the desire not to run one of the engines, the aircraft engines, when they're sat on the tarmac on the ground. They want to actually have their main engines off and then run an APU to provide air conditioning, to provide avionics, etc. So we're currently working with a US company in developing a Wankel Rotary APU for this business jet market. Again, to give you a size and how compact these are, this thing is 12 inches by 14 inches by 26, or 28, I can't remember. 26 inches. I mean, literally, it is that size and provides all the electrical power for the vehicle when it's on the ground, including the air conditioning avionics, but also to start the engine as well. So that's how small you can make these sort of rotary engine packages. And that's it, I think. Yeah, that's it. There you go.
Thank you very much. So let's have about 50 questions.
Thank you. That's a really good talk. Two things it has. One is you never mentioned anything about emissions and so on, so would be interested to see how this compares to existing engines. Another one I was wondering for myself is about how do you scale things up here? You know, make the diameter bigger? Do you make it deeper? Do you make multiple chambers? So just...
Yep, sure. So I'll take the easy one first, scalability. So scalability you can do both ways. So you can obviously increase the singular cubic capacity of the individual rotor. We only manufacture single rotor engines, and we do that specifically for efficiency. If you add multiple rotors in, you start to multiply the inefficiencies of the seal pack, etc. So where possible, try and use a single rotor as our philosophy. There are advantages with going multi-rotor with the balance of the engine. Which obviously some people like, and you see a lot of applications. Mazda, for instance, use twin rotors. Other people have used more. But yeah, so we found, or really the barrier with liquid fuels tends to be that 650, 700 cc limit. Tends to be as big you can go with the cubic capacity of a single rotor. As soon as you move into gaseous fuels, though, particularly hydrogen, then that unlocks. You know, all of a sudden you can have a much larger engine, and that's based on the sort of dynamics within the combustion chamber and what you can achieve within that with the flame front speeds. Obviously, there are other technologies that we're looking at, you know, things like, very interested in some technology in the analysis you're doing here with pre-chambers, which has obviously been used previously in rotors as well to try and get more energy into that combustion event to get that flame front moving and get more complete combustion, which could unlock maybe some of that. But yeah, for us it's single rotor. We would go multi-rotor if a customer really wanted, but single rotor for us. Increasing the power density, we could look towards turbochargers, but like I say, or superchargers, but then you start to add to that thermal challenge the Rotary has already, you know, as an engine. With regards to emissions, yeah, the Rotary engine emissions, we've done some work. In fact, we did a lot of work with Bath on emissions for an automotive project that we were working on in the UK. The emissions aren't as bad as you imagine that they would be. You know, there's a perception the emissions from Rotaries are terrible. They're not, but bizarrely what we found was the technology that we developed to help with the cooling of the rotor actually became quite a negative within that sort of emissions area, because we use, in effect, the blow-pass gas on the seal pack. So as the high pressure area of the engine in combustion, you get a natural blow-pass on the seal pack, which you would normally vent out or recirculate back into the engine. We seal that in, and we actually use that gas as our cooling medium for the rotor and recirculate it through an internal heat exchanger. So this system energizes as the engine starts to operate, but it means that until that energizes, the seal pack isn't working as efficiently as it could, and then when the engine shuts down, that seal pack de-energizes and releases all that gas out through the exhaust, including some of the lubricating oil. So that tended to be the bigger challenge we found, but overall, as not just from ourselves, but from other studies, you know, it is quite achievable to get these engines through Euro 6 and potentially improve it past then as well. No, I mean, it's been proven. So, you know, engines have run through the Euro 6 cycle, particularly at the moment, and we demonstrated that, you know, I mean, I think even the Mazda engines are actually very capable of producing very good emission, or very low emissions, shall I say. So it is there. It's just not, it's not been a concentration of the Rotary engine development, because in aerospace, as of now, most of the customers aren't, you know, our customers aren't that interested in the emissions. They're more interested in the other aspects of the engine, which is power density, etc. But we see this coming through, which is why we are, particularly with things like urban air mobility, where you're going to be flying over cities, and, you know, air quality is going to be a major issue. So yeah, that's why we see that changing the fuel to something like hydrogen or some other fuel would be a real advantage in those situations.
We can have a discussion about emissions. You'd be surprised. Any other questions?
Maybe a simple question for you, but
okay.
Why are you more fuel flexible than an IC engine? Is the fuel injection should be similar or not?
I wouldn't say we're more flexible than, I mean, we are an IC engine, so yeah. Yeah, so I wouldn't say we're more flexible than a reciprocating engine, but I think the advantage, as a technology, I think reciprocating engines can run on the same fuels we can. I think the difference is being able to run all those fuels in the same engine with no physical modification is the advantage that we have, particularly at the moment. So as I say, no physical modifications to the engine and no map modifications. We're not even changing the ECU map. the lambda sensors are able to take account of the differences and then actually change the map enough that the engine will operate on these multiple fuels. And this becomes, as far as we know, there's no reciprocating engines in the aerospace market that we work against anyway that has that ability. You always at least have to change the map in the ECU in order to operate in a different fuel. So.
Okay, any other questions?
Wow.
Oh, one more.
What's that? Where can I buy one? Is that?
Thank you for the nice presentation. I just wanted your comment on the noise levels for the rotary engines and how they comply with, say, the aviation standards, especially for the drones.
Yeah.
I guess the exhaust expander can reduce the noise levels, but then...
Yeah. So anybody who's sat next to a non-silenced or non-muffled engine, rotary engine, knows how loud they are. So they are very loud. There's a lot of energy in that exhaust. So yeah, you do have to silence them in some way. You have to put them through some sort of exhaust system to reduce the energy. What we have found is that absorption type silencing doesn't work because the energy destroys the material within the exhaust. I mean, literally, we've not found a material that can stand up to the shock waves coming out of the engine yet. You end up just blowing it all out of the exhaust after a period of time. So what we tend to use is like expansion chamber type exhaust systems, and they work quite effectively. And the other thing that a lot of people forget in aerospace is that the nature of the aircraft mean you've got spinning propellers, and those spinning propellers make a lot of noise. So I was talking about this the other day. We have a lot of customers that come to us and say, oh, we've got a VTOL helicopter style UAV, but we need the engine to be 70 dB, but their rotor disk is 105 dB. So you're like, well, just get the engine below your rotor disk, and then it's happy days. But it tends to not be the sort of overall noise energy, which you can do through a fairly simple exhaust system, though exhaust systems add weight, which is another aspect. It tends to be the frequency of the noise that tends to be the biggest challenge. So it's, as someone described it, as a screaming baby. And it unfortunately, they do tend to be at that sort of level that's at the sort of annoyance level when you're listening to them, which is subjective, obviously. It's not very scientific. But, you can listen to I think we all listen to a nice V8 automotive engine and think that sounds wonderful. Yet the noise level is quite high. If you stick a rotary engine next to that with the same noise level, you wouldn't think it sounded nice. You'd be like, that sounds pretty horrible. So yeah, but you get used to it. But yeah, so it is a factor. The other thing with UAVs, yeah, that level of my hearing is now non-existent, so it's all good now. So I can't hear screaming babies either, which is another advantage. But there you go. You tend to find also that a lot of these platforms are operating at altitude. So obviously, it's actually the design of the vehicle, the altitude it's sitting at. You take all these factors into account. Simple things like pointing your exhaust upwards. So there's a desire for vehicle manufacturers for some reason to point exhausts downwards. I don't know why. And you're like, well, no, just point it straight out the back or point it upwards. And obviously, noise is fairly directional. So you just have these sort of general comments with people. Yeah, for some reason, people just still want to point their exhaust down to the ground, which we've never quite understood. I think it's mainly for rain. They think the exhaust is going to fill with water and all that sort of stuff. But so yeah, it is a challenge with the packaging for sure, but it's completely mitigatable. I mean, the APU that I showed at the end there, I mean, that's 70 dB. And in comparison to a turbine APU, that sounds really nice. The turbine APU is a high-pitched whine. This sounds like a lawnmower on a Sunday, type thing. It's a much more pleasant sound. So.
Right. Anyway, you can hear one in a couple of months down in the test cells. I am expecting some complaints.
I think we are supplying it with the silencer, though. So.
Yeah. Everything's relative. Right, okay, if we can thank our speaker again, please.
Okay.